it says if you mix and I don't know what happened to the question here, why it's 5.2999999 instead of 5.3, but we'll go with it. Liters of hydrogen at 298 Kelvin in 1 atmosphere with 0.825 liters of oxygen at 298 Kelvin in 1 atmosphere. How many liters of H2O can be formed at that same temperature and pressure? So first off, let me note that this problem seems to have temperature and pressure constant. And the same. Interesting. But so otherwise, this can be worked in the same way as before. I'll use my color coding. We have information about the hydrogen. We have information about the oxygen. And we are trying to find information about the H2O, which should be a gas. And I think you're stuck with it since I know many people have already started the homework. But in the future, I will fix this to be a gas, and I apologize for that. But the process goes basically the same. So hydrogen, find the moles of hydrogen. Oxygen, find the moles of oxygen. Find out which one's the limiting reactant. I can see here that I've got a bunch more liters of hydrogen than I have of oxygen. So I'm guessing that oxygen will be the limiting reactant this time. But we'll see. So let's see, my ideal gas law is PV equals nRT. I need moles now. So I need to divide both sides by RT. And plug everything in. Let's see. Pressure, 1 atmosphere. Volume, I'm just going to round this to 5.3. My R value is always the same, 0.08206. And it looks like I need my line to be a little longer because my temperature is 298. And 1 times 5.3 divided by 0.08206 divided by 298. 0.217 moles of hydrogen. Same thing for oxygen. At the same temperature and pressure, but different moles. Now I've got only 0.825 moles. Sorry, 0.825 liters. And this time, I get 0.0337 moles of oxygen. Now, what do you think? Can you look at those numbers and tell me which one's going to be my limiting reactant, even though there's a 2-to-1 ratio here?
Oxygen.
It is going to be oxygen. I will prove that, though, just to be sure. So our process always says take your moles of reactant, do a mole-to-mole ratio. course, hydrogen stays the same number, but now it's moles of H2O. And for oxygen, since it's a 1 mole of oxygen to 2 moles of H2O, does double. .0674. We now know for sure that H2 is our limiting reactant. And, oh, that says, oh yeah, sorry, I should be down here. And this is the number of moles of H2O that can be produced. And so now for H2O, we can basically work the calculation backwards or in a slightly different way to figure out our liters of H2O. Solve the ideal gas law for volume. And once we do that, by the way, we'll reflect on our answer to see what's really going on in this problem. But we now know our moles of H2O. We know our R value. And for the first time, I'm just going to write R, since I have R a couple different places here, to save space. And my temperature is still 298. And my pressure is 1 atmosphere. So very similar to the last problem. I get 1.65 liters as my final answer. Now, let's come back to this idea. Well, first off, let me ask, are there any questions about what we've got here? Okay, so then let's come back to this idea that temperature and pressure for this problem are constant or the same. So the temperature is always 298 Kelvin, and the pressure is always 1 atmosphere. Okay. In that case, so you can actually think about you can see that you can actually work this problem from just using liters, meaning that if I take my liters of hydrogen and imagine that I can convert them into liters of H2O, I would see that I get exactly the same number. Whereas my liters of oxygen actually gets doubled because there's a 1:2 ratio there. And so so first off, this is a beautiful way to solve this. But if temperature and pressure are constant for the entire problem, then volume is proportional to moles. And you can see that because oxygen was my limiting reactant, I get double the liters of H2O because there's a 1:2 ratio here. Anyway, I didn't want to go too deep into that because I fear I may have added more confusion than I actually helped.
I mean, you can just multiply 0.825 times 2.
And you get the right answer for this. And that's because the temperature and pressure are constant in this problem. which I know is easier, but then so you have to feel comfortable using that approach. The longer approach that we just did always works.
Yeah, I have a question, Professor.
Go ahead, Mohammed.
So for the 5.299999,
Yes.
I didn't see it. Is it okay for us to round it up?
Yes.
Okay. Okay. All right. Thank you.
Sure. Yeah. No, that was. In fact, I don't know what happens for the computer to tell us that number. I'll have to look into that. 5.3 was what or 5.30 was what I'd hoped it to be there. Any other questions? Okay. So